Yeah. So I hope things are going well and that you're feeling good and rested and all those things. Today we're going to be going into sections 7.2 and 7.3. We're going to do both sections today. Worked out pretty well. At least I believe it worked out pretty well for the first period. In this presentation, we will first talk about section 7.2 with sample proportions and then move on to 7.3, which is sample means, also under the umbrella of sampling distributions. And I will have some examples that we will do, or that I'll show, so you kind of get an idea of how these things are used. And then that'll be the lesson. It went pretty well in first period. I do recommend that maybe don't try to write everything down from the presentation. There are some things that I will suggest that you write down for your notes, some formulas and conditions attached to those formulas, and when you can or cannot use them, or things that you need to check for. The formulas you will see today, I do believe they are on the formula sheet you will be provided for the AP test, but you still need to know when to use them, and what conditions need to be checked for. Right, so that's kind of like the idea is we're going to introduce these things. There's going to be some new formulas applying to proportions and means in a sampling distribution. And we'll discuss the conditions around them and see some examples. So before we do that, let's try to get my last few people here. And then we will share my screen. And present. Excellent. All right, and as usual, if you need time to write something down, raise your hand. If you have any questions, you need me to slow down, you need me to repeat something or explain something better than I have, please, again, tell me, raise your hand, shout out loud. Otherwise, notify me in some way, and I'll make sure that you get taken care of. All right, so we're gonna get started. So we are on section 7.2 and 7.3, sample proportions and sample means. And this is in chapter 7, sampling and distributions. So our objectives today, we need to find the mean and standard deviation of the sampling distribution of a sample proportion or sample mean. We're going to check the 10% condition before calculating the standard deviation of the sample proportions or sample means. Okay, so the 10% condition applies to both proportions and means. All right, we need to check for that before calculating standard deviation. Determine if the sampling distribution of sample proportions is approximately normal. Explain how the shape of the sampling distribution of a sample mean is affected by the shape of the population distribution and the sample size. If appropriate, use a normal distribution to calculate probabilities involving a sample proportion or sample mean. So that's our goal for today, is to learn about these things. So first, we're going to talk about sample proportions. Right? So the sampling distribution of p hat. Remember, p hat is our sample proportion. Something we're concerned about is how good is the statistic p hat as an estimate of the parameter p. Sampling distribution of p hat answers this question, right? We need to look and see what it looks like. Consider the approximate sampling distributions generated by a simulation in which SRSs of Reese's Pieces are drawn from populations whose proportion of orange candies is either 0.45 or 0.15. So we have two different populations of Reese's Pieces. And we want to think about, what do we notice about the shape, center, and spread of each? So here's our first distribution. This is a sampling distribution of the proportion of orange candies in samples, right? We did sample size of 25. We did 400 samples, it looks like. All right. The true value was 0.45. We got a p-hat of 0.48. We see the center is pretty darn close to what we would want it to be an unbiased statistic. If we increase our sample size to 50, same amount of samples, 400, same population parameter, 0.45, and we get a p-hat again that's pretty darn close, just a little bit less variation, less variability. Right, so, and then overall, the shape of both of these looks about approximately normal. If we go to the population whose proportion of orange candies was 0.15, we run the similar types of simulations. It was sample size 25 or 50, number of samples 400. We get a p-hat. For this, we get a, well, for this one sample, we had a p-hat of 0.24. But over the 400 samples, we do get a center pretty darn close to what we wanted, right, of the actual. Same thing happens with the other one over here. And in both cases, we still have something that looks approximately normal. So we get some results out of this, which is good. Right. These observations tell us some stuff, something about the shape. In some cases, the sampling distribution of p-hat can be approximated by a normal curve. This seems to depend on both the sample size n and the population proportion p. The mean of the distribution of p-hat is equal to p. This makes sense because the sample proportion p-hat is an unbiased estimator of p. That's what we saw in the dot plots in the previous slide. The spread for a specific value of p, the standard deviation, sigma p-hat, gets smaller as n gets larger. The value of standard deviation of p-hat depends on both n and p. Right? So the spread depends on sample size and the population proportion, but the center really only depends on the sample proportion. Right? Shape depends on both. There's an important connection between the sample proportion p-hat and the number of successes x in the sample. Right, so now we're back to a random variable x representing the number of orange candies in our sample. That would be considered a success. So p-hat is calculated by number of orange candies divided by the sample size, or the value of x, the random variable, divided by n. You don't need to write this part down. We're using this to get to the next thing that we need. In chapter 6, we learned that the mean and standard deviation of a binomial random variable x are these two formulas. The mean of the random variable x is n times p. Standard deviation of random variable x is the square root of n times p times 1 minus p. Since p-hat is successes divided by sample size, then we get 1 over n times x. We're just multiplying the random variable x by a constant 1 over n to get the random variable p-hat. It's a linear transformation with only multiplying. So therefore, the mean of p-hat is 1 over n times np, right? The mean of that we expect, right? So p-hat is an unbiased estimator of p. Mean of p-hat is p. Standard deviation is equal to 1 over n times the square root of np times 1 minus p, which is equal to the square root of np times 1 minus p over n squared, which is equal to the square root of p times 1 minus p over n. So we end up with this formula. Right. As sample size increases, the spread decreases. This is a result from section 7.1. Larger sample size, less variability, less spread. Oops, sorry. Yeah, that's good. All right, and so then we get this. Here's those actual formulas in a nice written out manner. So if we choose an SRS of size n, right, from a population of size n, capital N, with proportion p of success, then we let p hat be the sample proportion of successes. Then the mean of the sampling distribution of p hat is p. Right? It's just equal to the whatever proportion it was, the parameter from the population. The standard deviation of the sampling distribution of p hat is the square root of p times 1 minus p over n. Essentially, the probability of success times the probability of failure divided by sample size. And then we take the square root of all that. And again, we can only find the standard deviation if the 10% condition is satisfied, meaning that our sample size is less than or equal to 10% of the entire population we're sampling from. As n increases, the sampling distribution becomes approximately normal. Before you perform normal calculations, check that the normal condition is satisfied. Right? That means we're checking the large counts condition. The number of successes, n times p, must be greater than or equal to 10, and the number of failures, n times 1 minus p, needs to be greater than or equal to 10. Right? This should be in your notes. This is the conditions and the things that we need for sample proportions. Right? Please raise your hand if you need a moment to write this down. So now we're going to look at an example. Right, so in our example here, we have about 75% of young adult internet users, ages 18 to 29, watch online videos. Suppose that a sample survey contacts an SRS of 1,000 young adult internet users and calculates the proportion p hat in the sample who watch online videos. So before we jump into the problems, let's just identify the values we were provided. All right. So we have 75% as one of our values. 75%, this is the parameter p, and that's the proportion of the population. And we're assuming that this is true. Right, we're going to suppose that a sample survey contacts an SRS of 1,000 young adults. 1,000 is the value of n as far as our variables are concerned. Right. And those are the only values we're given. Right, p hat is the sample proportion. And now we need to calculate stuff. So for number one, what is the mean mu of p hat and standard deviation sigma of p hat of the sampling distribution p hat? Well, luckily the first value here to calculate is the mean of p hat, and that is just equal to p, which is 0.75 as a decimal. It is much more common to write your proportions as decimals rather than percentages. Decimals are just ready to work with. Right? We can do calculations with them. So that's mean. We're done with that one. Now, before we can do standard deviation, we have to check the 10% condition. We need to confirm that that's met. Sometimes you have to actually show the numbers. Sometimes you just have to make a statement that's obviously true. In this case, that's kind of what we'll do. So our SRS of 1,000, right? The SRS of 1,000 young adult internet users is not more, less than 10% of all young adult internet users So standard deviation of the sampling distribution of p hat is sigma of p hat is equal to the square root of p times 1 minus p over n, which is equal to 0.75 times 0.25 all over 1,000, which gives us 0.0137. And we have found the mean and standard deviation. All right. Any questions on this part of the problem? Anything I can clarify? All right. So the next part is check the large counts condition. All right, and by doing that, we're answering is the sampling distribution of p hat approximately normal. Right. So we need to check if NP is greater than or equal to 10, and that n times 1 minus p is also greater than or equal to 10. Well, NP is 1,000 times 0.75, which equals 750, which is greater than 10. So that's good. And 1,000 times 0.25 is equal to 250, which is also greater than 10. So our large counts condition has been satisfied. Right. So since the large counts condition is met, that means the sampling distribution of p hat is approximately normal. Sorry if you guys can hear, like there's doing some weird construction above our condo, so I apologize. So that's the answer to question 2. Last question. if the sample size were 9,000 instead of 1,000, how would this change the sampling distribution? When they ask that question, it's like, what effect is it going to have to how we describe the distribution, right? Is it still going to be normal? Is it going to change the shape? What's going to happen to the spread, the center, those types of things. All right, and so to answer that, right, the sample size does not change the mean. Remember, the mean doesn't depend on n and p, it just depends on p, the sample, or the population proportion. So for this one, right, the mean will still equal p, will still be 0.75. All right, the standard deviation is going to change by decreasing by a factor of 3. And we know this, or we can kind of estimate this, because we're increasing from 1,000 to 9,000 as our SRS size, and that's 9 times the simple random sample. Square root of 9 is 3, and we're using the square root in the standard deviation. All right, so then our standard deviation of p hat goes to 0.75 times 0.25 over 9,000, and we get where did I put that? 0.046. Right, and the sampling distribution of p remains approximately normal. Okay. Is there any questions or anything I can clarify about this example? So we need a moment to write anything down from this example. Okay. So then back to our presentation. And we're moving to sample means. Okay. When we record quantitative variables, we are interested in other statistics such as the median or mean or standard deviation. Sample means are among the most common statistics. Consider the mean household earnings for samples of size 100. Compare the population distribution on the left with the sampling distribution on the right. What do we notice about the shape, center, and spread of each? Well, the population distribution is skewed to the right. Right? The mean looks to be about, 80, 75, 80, right, as far as like thousands of dollars. Right? That's what this is indicating here. The sampling distribution, samples of size 100, the mean is about the same place as it is over here. However, now this is approximately normal and much less varied. But it's kind of interesting that the mean between both of these is about the same place, which should indicate, right, that we have an unbiased statistic. right? And we get this little note here, because both histograms use the same scales, we can directly compare this with the one over here, which is always nice. So again, we get some useful results out of just kind of comparing these things, right? When we choose any SRSs from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution. That's what we just saw. So here are the facts. Again, this is something you want to have in your notes. So the sampling distribution of a sample mean, right? Suppose that X bar is the mean of an SRS of size n, drawn from a large population with mean mu and standard deviation sigma. Then the mean of the sampling distribution of X bar is mu. It's just the same mean. So in both of these situations, sample means and sample proportions, the mean of that statistic is the mean of the population because they're unbiased statistics. The standard deviation of the sampling distribution of X bar is sigma, the standard deviation of the population, divided by the square root of the sample size, n. And once again, as long as the 10% condition is satisfied, the standard deviation is connected to the 10% condition for both sample mean and sample proportion. You have to check that 10% condition to ensure that you can actually calculate the standard deviation. You could get a result for standard deviation no matter what, but if the 10% condition is not satisfied, you found a number that you can't use. And please note, these facts about the mean and standard deviation of X bar are true no matter what shape the population distribution has. Right. This is true no matter what shape a population is. Can you please raise your hand if you need a moment to write anything down from this slide? So if we sample from a normal population, we have some results here. We have described the mean and standard deviation of the sampling distribution of the sample mean X bar, but not its shape. That's because the shape of the distribution of X bar depends on the shape of the population distribution. In one important case, there's a simple relationship between the two distributions. If the population distribution is normal, then so is the sampling distribution of X bar. If we start with a normal population, we get a normal sampling distribution. This is true no matter what the sample size is. So if we start normal, we get normal back out, regardless of sample size. And that's stated here. Right. Suppose that a population is normally distributed with mean mu and standard deviation sigma. The sampling distribution of X bar has the normal distribution with mean mu again, and standard deviation of sigma divided by the square root of n, again where n is the sample size, and provided that the 10% condition is met. But we just know going into it that we're going to end up with something normal because we started normal. Does anyone need a moment to write anything down from this slide? Okay. So then we're going to look at an example. All right, so in this case, we have the length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, with mean 266 days and standard deviation 16 days. Jeez. Suppose we choose an SRS of 6 pregnant women. We're going to let X bar equal the mean pregnancy length for the sample. So now, again, let's see what values we have given here. We know that this is approximately normal with a mean That's going to be mu of 266 days and a standard deviation, sigma of 16 days. We have an SRS of 6, that's n, right? And x bar is the mean pregnancy length for the sample. We want to calculate the mean of x bar and standard deviation of x bar of the sampling distribution of x bar. But again, we have to check that 10% condition before finding the standard deviation. So we'll do number 1 here. The mean of x bar is just equal to the mean, which is 266 days. Yeah, that doesn't change. All right, and 10% condition. Well, since 6 is less than 10% of all pregnant women, pretty safe to say that there, at any point in time, there's more than 60 pregnant women. So I'm pretty safe in saying this is less than 10%. So then the standard deviation of x bar is equal to sigma divided by the square root of n, which is 16 over the square root of 6. And that gives us approximately 6.532 days. Right, so we've got our mean and standard deviation. We checked the 10% condition. We are good with question 1. Question 2 now. Find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. All right, so we want to find the probability that x bar is greater than 270. Okay, so in this case, right, we started with a normal distribution. Right, we were told that the distribution is approximately normal of our population. So we know that this has to be approximately normal, so we can use normal calculations, which means we have to standardize this score first. Right, we're going to use table A. Right, so we get z equals 270 minus 266 divided by 6.532, and we get a z-score of 0.61. Okay, so now we're going to go up here. We'll say, okay, well, this has to be equal to the probability of z being greater than 0.61. But remember, table A only gives us less than or equal to probabilities, so we're going to use the complement rule. Say that this is equal to the probability of the probability of z being less than or equal to 0.61. Okay, so we got to go to table A, which I have over here, and we need to find 0.61. The first part of the table is all negative. Go to the second part of the table, and we have 0.6 right here, 0.1 right here, and we have 0.7291 as the proportion of the area under the curve less than 0.61. Right, so That means that this, the probability here, is 0.7291. So we have 1 minus that. And we end up with 0.2709. So the probability of the mean pregnancy length for the women in this sample to exceed 270 days is about 27%. Is there any questions about how I did either of these calculations or any of these calculations or where I got the numbers from? Excellent. Okay. So then we'll go back into our presentation. The last thing we need to cover for this is the central limit theorem. Most population distributions are not normal. What is the shape of the sampling distribution of sample means when the population distribution isn't normal? Right. Well, a remarkable fact is that as the sample size increases, the distribution of sample means changes its shape. It looks less like that of the population and more like a normal distribution. This is good news. We know how to work with normal distributions. When the sample is large enough, the distribution of sample means is very close to normal, no matter what the shape of the population distribution has, as long as the population has a finite standard deviation, meaning it has a standard deviation that has a value attached to it. So if we draw an SRS of size n from any population with mean mu and finite standard deviation sigma, the central limit theorem says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. Okay, so as long as this large condition is met, then we can use normal calculations, even though our population wasn't normally distributed. So we will sum this up on the next slide here. So again, even when the population is very non-normal, the sampling distribution of the sample mean often looks approximately normal with sample sizes as small as n equals 25. So we have the normal large condition for sample means. This first paragraph is what we knew before. If the population distribution is normal, then so is the sampling distribution of x bar. This is true no matter what the sample size n is. So we start normal, stays normal. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases if n is greater than or equal to 30. So we check the condition, like if our sample size is greater than or equal to 30, then we can use normal approximations, which is awesome because we know how to work with those. The central limit theorem allows us to use normal probability calculations to answer questions about sample means for many observations, even when the population distribution is not normal. Please raise your hand if you need a moment to write anything down. So in a nutshell, sampling distributions, proportions versus means. With a sample proportion, right, the mean will be equal to the parameter p. Right? The mean of p hat is equal to p. Standard deviation, as long as the 10% condition is satisfied, will be equal, the standard deviation of p hat is equal to the square root of p times 1 minus p divided by n. Again, where p is the parameter, or the proportion of the population, and n is the sample size. And then as n increases, the sampling distribution becomes approximately normal. Large counts condition must be satisfied to do normal calculations. Now this large counts condition is not the same as the central limit theorem. Large counts is saying that there's at least 10 successes and at least 10 failures. Sample means, right, the mean of X bar is the mean of the population. They're unbiased statistics. And as long as the 10% condition is satisfied, the standard deviation is equal to the standard deviation of the population divided by the square root of the sample size. If the population distribution is normal, and so is the sampling distribution of X bar, the central limit theorem says that when n is large, greater than or equal to 30, sampling distribution of the sample mean X bar is approximately normal. So we have these conditions that we need to check as we go along through these calculations. We have 10% condition for both. And we have the large counts condition for sample proportions and the central limit theorem that we can apply to sample means if our parent population is not normal. Does anyone need a moment to write anything down from these or from this screen? So in summation, we can now find the mean and standard deviation of the sampling distribution of a sample proportion or a sample mean. And in both cases, we know we need to check the 10% condition before calculating a standard deviation. We can determine if the sampling distribution of sample proportions is approximately normal. Right? We know that for a sample mean, the distribution is approximately normal if the parent population was normal, or if the central limit theorem is met. And for a sample proportion, right, we know that it's approximately normal if the large counts condition is met. We can explain how the shape of sampling distribution of a sample mean is affected by the shape of the population distribution and the sample size. Right? Again, this goes back to the central limit theorem. And if appropriate, we can use normal distribution to calculate probabilities involving sample proportion or sample mean. And that is the end. Is there anything I could go back to in the presentation or in the examples, anything you'd like to see again or have a better explanation of? All right, so then with that, tomorrow we'll be doing some practice problems and some opportunities to put these things into practice and with both sample means and sample proportions. I do recommend, again, I highly recommend doing practice problems if you have the availability and time to do so. I should have the solutions for the practice problems available later this week. That's for sections 7, 1, 2, and 3. And other than that, if there's anything else I can help you with, if you have any other questions or need clarification on anything we covered, please stick around and let me know or send me an email. Other than that, I'll see you guys tomorrow. Have a lovely rest of your day, and we'll see you later.